We're about to work through some practice problems. Now, for the best effect, you should always try these problems by yourself first. If you're watching this video for the first time, you can use that pause button when you see a problem and try it yourself. Unpause to see if we agree. An alternative is you can follow the links below and you can find a copy of these problems which you can work out at your leisure. All right, let's get going. Use Newton's method to approximate the value x for which the curves f of x equals x squared and g of x equals 3x plus 9 intersect. Using 3 as your initial guess for x0, determine x2. All right. Now, notice there's something a little bit different here. Now, normally when we talk about Newton's method, the goal for Newton's method is we're after roots. So that is to say, if we have a drawing here, so let's just do a quick sketch. We have a function, and the goal is to say, hey, where are we hitting the axis? So that's our normal goal. Now you notice on this problem, it says you're not after a root, you're after for where two curves are crossing, they're intersecting. So you say, okay, so how do we turn this crossing problem into a find a root problem? Well, to say that the curves intersect is telling us that we want f of x to equal g of x. Now, we know what f and g are, so we can say, well, that means we want x squared to equal 3x plus 9. Or we want to know when does x squared minus 3x minus 9 equal 0. So this is the function we're going to apply Newton's method to. We'll call it h of x. Now, let's do a quick recap, reminder of how Newton's method works. So it says, look, you have a function. This is our function in our case, but in general you have a function, and you have a guess. We'll say this is our current guess. The goal is make a better guess. So what do? You go up to your function and say, you know, right now this function nearby looks pretty flat, looks like a line, and we can follow that line down, and wherever that line hits, well, that would be a pretty good next guess. It would be probably a better guess. So we say, all right, do we know that line? Well, yeah, it's the tangent line. And we say, okay, so what did we do? We write down the formula for our tangent line. Y is equal to the value of the function at our current guess plus the derivative of the function at our current guess times x minus xn. To follow it down means that we're going to have y be 0, and we're going to have our x value becomes our next guess. Okay, so if you put in 0 for y, and you say that's your xn plus 1, you rearrange it, and you get to the following. And I call it f, but I can call it anything. Xn plus 1 is equal to xn minus the value of the current function over the derivative of the current function. Okay, so that's your basic recursion. If you remember that, you're like 90% of the way there. Okay, now let's apply it to our specific case. We have our function h of x, that x squared minus 3x minus 9. And we can also note that h prime of x is 2x minus 3. All right, so our recursion says to find the next guess, we're going to take our current guess, xn, minus the value of the function. So that's xn squared minus 3xn minus 9, divide by the value of the derivative, 2xn minus 3. All right, now some good news. We know our first guess because they told it to us. And what are we looking for? We're looking for our sort of two guesses down the road. So our initial guess is 3. So x0 equals 3. So x1 would be 3 minus. Okay, so 3 squared is 9. 3 times 3 is 9. 9 is 9, the 999. 2 times 3 is 6, minus 3. So that's 3 minus, those cancel. So we really have a minus 9 over 3, or that's 3 plus 3, which is 6. And so we're like, yes, 6. That's one of our answers. But that's x1. Oh, they were devious. They put what should be x1 as one of our options. Oh, so tempting. Oh, those sneaky test writers. Because what are we looking for? x2. You got to do it again. The technique is so nice, we do it twice. So let's plug it in. 6, make sure you plug it in everywhere you see. So 6 minus, upstairs, 36, 6 squared. 3 times 6, 18, and 9. Downstairs is 2 times 6, which is 12, minus 3. Okay, 36 minus 18 minus 9. What would that be? That would be 9. 12 minus 3, also 9. 9 ninths, 1. 6 minus 1 is 5. Ah, now that's x2, and that is also an option. So our answer is 5. All right, good. Okay, so make sure you pay attention, right? Don't be tempted. They're going to put very tempting answers here. But the key is know your recursion and carefully work it through. And don't rush your algebra and arithmetic. They know the common algebra and arithmetic mistakes. And so they're going to anticipate people making them. And so be careful. Get your points. Do great. Find the sum k equals 2 to 10 of 3k minus 5. So we're adding up a bunch of numbers. Remember that this capital sigma is shorthand for sum. So we're adding up a bunch of numbers. And we have some options. And we say, okay, well, it's not obvious how to go from one of these to figure out which that is. We actually have to do the problem. Now, there's a couple of ways we can approach it. So let's talk about some options that we have available to us. Now, one way we can do this is to literally write down all the numbers and add them all up. That might take a while, but let's go ahead and write down a few numbers and see where we're at. So start with plugging in k equals 2, because that says start at 2. 3 times 2 is 6, minus 5 is 1. So the first number is 1. Plug in the next number, which would be 3. 3 times 3 is 9, minus 5 is 4. So 1 plus 4. Plug in the next number, that'll be 4. 3 times 4 is 7, minus 5. Sorry, 12 minus 5 is 7. I'm sorry, my computation was going too fast. I got to slow down. Okay, and we'll do a dot, 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 saying the pattern continues because I don't feel like writing down a bunch of numbers. And all the way up to 10. 10 times 3 is 30, minus 5 is 25. Okay, so you could add all of those numbers up, and you would get the answer. Let's talk about some other things that we can do, because I don't want to focus on the brute force approach, because the brute force approach, while it works, it's easy to make a small arithmetic mistake, and that can get us into trouble. So I want to talk about things that are a little bit more not brute forcey. Okay, so here's sort of two options. Okay, so brute force, we'll just mark it down, is just, whoops, I can spell brute force. Add all numbers up by hand. Will you get the right answer? Yes. Do you run the risk of an arithmetic mistake? Yes. And so that's why we want to be a little bit careful. Okay, so let me talk about some other options. Another option you have is to say, look, this sum is really 3, the sum, k equals 2 to 10, k minus 5, sum k equals 2 to 10 of 1. And then say, let's talk about sums that we know. And so there's some basic sums that are good to have, and anything more exotic than the following two will be given to you. 1 to n of 1, that says you add 1 plus 1 plus 1 plus 1 plus 1. If you add it up n times, you get n. Similar, if you add 1 to n of k, so 1 plus 2 plus 3 plus 4, well, that's equal to n times n plus 1 over 2. So you say, hey, let's do the same idea here. But be a little bit careful here. And I want you to pay attention, right? Notice, where do we start? We don't start at 1. We start at 2. So pay close attention, because that's an easy place to make a mistake. But that's okay. So it's easy to fix. So here's how we can think of it. Well, it's really like the sum from 1 to 10 of k, but we added this extra term at 1, so we're 1 off. Because when k equals 1, you get 1. And in a similar way, you get 5, sum k equals 1 to 10 of 1, but again, we're just 1 off. We need to correct because we started at 2, not 1. And now, apply the formula. So that's 3. So 1 to 10, according to this, be 10 times 11 over 2. And then you're going to subtract 1 minus 5. And here, it'd be 10 minus 1. Okay, well, 10 times 11 over 2. Well, think about it as 10 over 2 is 5. Times 11 is 55 minus 1. Well, that's really 54 times 3. And here, this is minus 5 times 9. And so that's 45. 3 times 54, that's equal to 162. Subtract 45. And now you say, well, 162 subtract 45 is 117. Okay, so there we go. That's it. And if you did the brute force, you get the same. But I do want to point out one other thing you can do. And here's a fun approach. Now, this only works if what you have has a very special form. So if all the differences are the same, so if all differences are equal, now that means, in other words, consecutive terms, 1 to 4, 4 to 7. This has a very particular name. It's called an arithmetic sequence. It just means that we're adding the same quantity at each time. And they all have the exact same look. They all look like the sum from k equals, sum c up to sum d of a times k plus b. They all look like this for various choices of a, b, c, d. Now, if that's true, here's the fun thing. What you can do is you can add the first number plus the last number, divide by 2. So in other words, it's like average the first and last together, and then you times it by the number of terms. And if you run that computation, that's the sum. It's actually the way that this is derived. The way it's derived is you think of like 1 plus 2 plus n, but then you start 1 plus 2 plus n backwards, you add them up, and then you say, oh, it's like the first plus the last all the way down, and now but you double count, so you divide by 2, and then you say, how many did you add? Okay, so what was our first term? 1. What was our last term? 25. So 1 plus 25 divided by 2. How many terms are there? Well, you started at 2 and you go to 10. And great news is we have fingers, right? So here we go. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that means we used 9 fingers. So there were 9 terms. So 1 plus 25 divided by 2 times 9. 1 plus 25 divided by 2 is 13. So 13 times 9 is 117. So that's another way to do it if you happen to be in the cases where you're in an arithmetic sequence. So it's a nice little shortcut. Yes, it doesn't apply everywhere, but where it does apply, it's nice to have a check, or if you will, a speed run. All right, well, fun. Woohoo! And don't worry, if you forget all of this, brute force is handy, right? It's still there, and it's always an option. Use the graph of y equals f of x in the picture below. Hello, picture. And we're going to do a Riemann sum to estimate the area under y equals f of x from 1 to 7. So it's like, see how we have this area? We're supposed to estimate it by a Riemann sum. We're going to use 3 equally sized intervals and use the left endpoints. Okay, so now 1 to 7. So we're starting at 1, going to 7. So we say, first off, how many intervals? 3. Now, why is 3 so popular? Well, that's about how many numbers we can add before we start getting nervous about making mistakes. So that's probably why. But it's enough to sort of test the ideas. So we're splitting it up. Now, it's not hard to see if you go from 1 to 7, and we break it up into 3 parts, you'd have widths of size 2. So you go 1 to 3, 3 to 5, 5 to 7. Now, we've split up our 1 to 7 to 3 equal intervals, and these are our widths. So we have widths of 2. Now, for each interval, we have to get a height. So how do we get a height? Well, that's where they're going to specify. So here it's telling us to go with the left endpoint, which means for each interval, we're going to go to the left endpoint and say whatever the height is at that's our rectangle. So there we go. There's the rectangle estimates the first part. Between 3 and 5, we're going to go to the left, and we're going to use that height. It's going up and across. This one is the area for the second part. And from 5 to 7, we go to the left, go up, and then we say, okay, that's our rectangle for the third part. So those are the pieces that we're going to use to estimate our area. So we have our first rectangle is a 2 by 3 plus a 2 by 5 plus a 2 by 6. Well, that's 6 plus 10 plus 12, which is 28. Okay, 28. And so our answer is 28. And there we go. And in this case, we were able to use the information about the function. Instead of giving it as a chart, they gave us as a graph, and that's all right. It's the same philosophy. And sometimes when you see the picture, it's a little bit easier to understand. Oh, Riemann sums are about adding up rectangles? Yes. Has that always been the case? Yes. Oh, it makes so much more sense now. Yes. All right, good. Well, I hope we have more like this on the exam, right? Well, maybe. Find the integral from -1 to 1 of 2 minus pi sine of t cubed over 1 plus t squared dt. Well, part of this looks not too bad, and part of it is like, Okay, so first off, let's take advantage of the nice plus sign. Well, in this case, it turns out it's a minus sign, and which is this piece up here. A plus or minus upstairs is good news. We like that, because what it's really telling us is that we have the ability, should we choose, to pull it apart. And we're going to make that choice. So we say, this integral, we're going to separate into 2 pieces. So we'll have 2 integral -1 to 1 of 1 over 1 plus t squared dt, and then minus pi integral -1 to 1 of sine of t cubed over 1 plus t squared dt. Right, okay, cool. Now, one of these 2 integrals seems pretty straightforward. 1 over 1 plus t squared. That feels like something we've kind of done before. And that's because we've kind of done it before. 1 over 1 plus t squared, that's our arctangent. So I say, hey, this is a nice one here. And what can we do? Well, actually, we can take advantage of symmetry. Notice how we're going from -1 to 1. Let's first notice that we can double this and go from 0 to 1. And you might say, wait, what symmetry are you talking about? Well, this is an even function. And for even functions, if you go from -a to +a, it's twice of going from 0 to a. And that's because you have this nice symmetry across the axis. So an even function has this kind of thing where you can flip it across. And so you say, if I go and add up things on the left, it matches things on the right. That's the sort of the spirit here. And so we can just simplify. Now you might say, how does that simplify anything? It puts a 0. We love the zeros. Like zeros are like, yeah, that's our jam. Excuse my language, but they are our jam. And so we say, okay, so this is like 4 arctangent of t evaluated from 0 to 1. And arctangent of 0 is 0. Arctangent of 1 is pi fourths. So that's 4 times pi fourths, which is pi. Okay, now that's the first one. Now we have another part, though. We got to talk about that. Now this one looks not tempting at all. Sine of t cubed divided by 1 plus t squared? That's outrageous. How do they expect us to know this integral? Or do they? Yeah, so that's actually a really good question. Are we expected to know this integral? Or should we be thinking of doing something else? Think about what we said here. This is an even function. What kind of function is this one? It's a very peculiar function, a very strange function, unusual, weird. Some people might even call this function odd. It's an odd function. They might say, wait, well, hold on, what is an odd function? Well, an odd function is when you have f of negative t is negative f of t. So this is odd. So if you plugged in here, negative t quantity squared, same as positive t squared. But here, negative t cubed is negative of t cubed, and sine, the negative comes out. Now you might say, well, okay, so how does that help us? Well, it tells us a little something. I'm going to make some notes over here. What does it mean to be even? F of negative t is f of positive t. Now, in terms of our picture, what it tells you is if you're doing something on this side, you're going to do the opposite on that side. So if you're going from, say, negative a to positive a, what happens to your areas? They cancel. And so integral from negative a to positive a of an odd function will always be 0 by symmetry. And so that's why it's nice if you ever see bounds like negative a to a and say, hey, do I have an odd function? Because that can make this integral super easy. And that's what we are in this case. And so we're like, nice. Okay, so what's our answer? Well, we have pi, subtract pi times 0. And so that means, what are we left with? We are left with pi, which is one of our options. Woohoo! Nice, nice. All right, so yeah, know your symmetries, even and oddness. It can be a really great tool and really help simplify things dramatically in case of you have really unusual functions. It's kind of a clue. If you have like a really, really ridiculous thing, you should be thinking like, I wonder if there's some symmetry. Sometimes substitution works, but the symmetry is also a pretty good thing to have in your pocket. Find the value of c which satisfies the mean value theorem for derivatives for the function f of x equals square root of x on the interval 3 less than or equal to x less than or equal to 12. All right, now we have a clue, right? We're told mean value theorem. But actually, there were two mean value theorems, and so it goes out our ways to say, hey, it's the derivative mean value theorem. So what does the derivative mean value theorem say? Well, that says the following. It says that if you have a function which is differentiable and continuous, in other words, a reasonable function, we're not going to give you one that's not unreasonable. It says f prime of c, now this is your instantaneous rate of change, is equal to f of b minus f of a over b minus a. This is your average rate of change with c between a and b. All right, so that's the statement of the mean value theorem. So it says, hey, there's some time when your instantaneous rate of change is your average. So at some point, your rate of change has to be matching the average. Now, how do we verify this, or how do we find the value? Well, we need to find our average rate of change, we need to set our derivative, and then we need to solve. Okay, so here we go. Well, we can find our f prime of x. We'll do that really quickly. So in our case, f of x equals square root of x, which is, by the way, our calculus-friendly way of writing that is x to the 1/2. Calculus-friendly because it's friendly with the rules. So we bring the half down, x to the minus 1/2. Or, bring it back into algebra, 1 over 2 square root of x. All right, so that's our term we're going to use on our left-hand side. Let's do our average rate of change. So in our case, a and b are 3 and 12. So we have 1 over 12 minus 3. That's 1 over b minus a. And I don't know why I said 1 over that, but f of 12, so that's square root of 12, minus f of a, square root of 3. Okay, now there's a few things we can do. This is 1/9, 12 minus 3. Now square root of 12, 12 is 4 times 3, and square root of 4 is 2, so this is really 2 square root of 3 minus square root of 3, or if you like, that's just the square root of 3. So that's the square root of 3 over 9. All right, so this is our instantaneous rate of change. Here is our average rate of change. And now we're going to set them equal. And fingers crossed, we'll solve and we'll get something which is a reasonable number. So 1 over 2 square root of x is going to be equal to square root of 3 over 9. And once we solve for that x, if it's one of these, we're done. Okay, well, I don't like fractions. I think I had a bad experience once when I was a kid with fractions, and I'm just like, fractions, So I try to avoid fractions. So here we'll do a little bit of cross multiplying, help clear our fractions out. And doing that leads us to 9 is equal to 2. And we have square root of 3 times square root of x, so we can just write that as square root of 3x. And all right, well, what can we do here? We can square both sides, and that gets rid of the square root. So 81 is equal to 4 times 3x. And wow, we're almost there. So that tells us then that x is equal to 81 over 12. Well, 81 has a factor of 3, as does 12, so we can divide out top and bottom by 3. So that's 27 divided by 4. Now, let's see. What does 27 divide by 4? Well, that would be 6 plus 3/4, right? Yes? So 24 and 3/4. or 6.75. So our answer is D. Now, of course, if we wanted more precision, we can add two zeros, and we have engineering levels of precision, 6.75. And but even here we can kind of tell it's bigger than 6, it's smaller than 7, it's got to be D. And so, great, there we go. All right, so if you see a mean value theorem for derivatives, that's the mean value theorem for derivatives. Okay, on a side note, you might say, wait, what's the other one? We don't need it for this problem, but just so you know, the mean value theorem for integrals has the following. And it looks very similar. It basically says f of c is equal to 1 over b minus a, integral a to b, f of x dx. And that's with c between a and b. So this is, again, another case of saying, hey, at some point, the function has to match the average value of the function. Here, this says the rate of change of the function has to match the average rate of change. So those are the two different mean value theorems. The one that we usually see more often is the mean value theorem for derivatives. But all right, okay, I think we've done this problem, and we're on ready for the next one. Oh yeah. Find the limit as n goes to infinity of 2 over n, sum k equals 1 to n of 2 times 2k over n cubed minus 3 times 2k over n. Okay, now let's talk about what we're not going to do. Well, we're not going to panic, we're not going to skip, and we're not going to do l'Hopital. Okay, so l'Hopital, this is not the right place for it. What kind of thing do we have? What do we see before us? Well, it kind of gives it away in the hint. It says, hey, this looks like a Riemann sum. So we say, oh, so in other words, this is like an area. And so if we can just figure out, hey, what area is this trying to represent? If we find that area, we're good to go. Okay, so let's talk about what Riemann sums look like in general. And there's a very particular case that we usually almost always see. And it says the following. Suppose you want to have the Riemann sum for f of x for 0 less than or equal to x less than or equal to b. Now, and with the right endpoints. Not the wrong endpoints, the right one. No, here, right versus left. So then what you have is a sum, and you have n rectangles, so you have n parts. Your widths are all going to be the same. So you take your b minus 0, which is b, divide by n, and then you have your f, your function. So this is your height, this is your width, this is going to be your height. So it's f, and now what you do is you want to move over to the right endpoint of the kth interval. So you do that by multiplying b times k over n. All right, so this is the generic formula to know. So we want to sort of extract that. And so there's a couple of things that we have here. This part right here, that's acting like this b over n part. All right. So this other piece right here, this is acting like our f of bk over n. Now, here's the cool thing. You see how we have this bk over n? You say, well, that's like here and here. So think of that as your x. See how that is like f of this, f of x? What is our function? So this is a Riemann sum for f of x, which is 2x cubed minus 3x. Okay, so that's what's the interval? Well, we said 0 to b, and here we have 2. So this is 4, 0 less than or equal to x, less than or equal to 2. Now there's another way to sort of think about 0 and 2, which is to say, think about what happens at the very smallest point. So think k equals 1, now let n get big. 2 over n goes to 0. So one endpoint is 0. Other endpoint, k equals n. You have 2n over n. 2n over n is 2, which goes to 2. So 0 to 2. So now it's like, whoa, we're looking for the area under the curve 2x cubed minus 3x between 0 and 2. We can just integrate. We have the technology. All right, so this is going to become the integral 0 to 2 of 2x cubed minus 3x. Well, this is add 1 to your powers. So you get 2x to the 4th divide by 4 minus 3x to the power 2 divide by 2. And you plug in from x equals 0 to 2. When we plug in 2, well, we have 2 divided by 4 is 1/2. 2 to the 4th, 2, 4, 8, 16. Okay, so that's times 16 minus 3/2. And then 2 squared is 4. And then when we plug in 0, we have 0. Okay, so 1/2 times 16 is 8. 3/2 times 4 is 6. 8 minus 6 is 2. So our limit is 2. Okay, good, good. And notice we didn't have to actually do the limit. It was a matter of interpreting the limit. And so that comes down to, do we understand Riemann sums? And we can say, we say here's the widths, here's our function, and we can rewrite that function in terms of x. And then once we understand our endpoints and our function, integration, life is good. It's not as scary as we thought. That often happens with math problems. A lot of times they look scary. We have to have a small panic attack. And it's okay to be nervous. Just take a problem and and remember, the instructors like you. They want you to succeed. I know it's a crazy idea, but it's true. They want you to succeed. So they're not going to give you something you can't do. They're going to give you something that will test you and stretch you, but you will be able to do it. Okay, good. Well, let's move on to something a little different. Find the following limit. If you use L'Hopital's rule, make sure to include justification for why you can use the rule. Now, when we talk about justification for L'Hopital's rule, what we're really talking about is we want to see 0 over 0, or we want to see infinity over infinity. So those are the times when we can use L'Hopital's rule. And so if you just start taking derivatives without justifying it, we're like, hold on, you need to explain why. All right. So here we go. We have the limit as x goes to 0 of 1 over x cubed times the integral x to 3x sine of t squared dt. Okay. Yeah. What? Now, if you look, this already has a fraction. So this is the limit as x goes to 0. And we could write it as the integral x to 3x sine of t squared dt over x cubed. Now, let's talk about what's currently happening with this limit. When we plug in 0, right? Because you should always, first thing you should do is plug in. If you have an answer, you're done. It's only when you don't have an answer that you have to put in and do some more work. So downstairs, 0 cubed, 0, that's no problem. Upstairs, you have integral 0 to 0 of sine of t squared dt. Now, we don't know what the integral of sine of t squared is, but we do know what it is when we talk about 0 to 0. When we have something going to from the same start and stop, what's the total? It's 0, because if we were thinking in terms of area, there's no width, right? If you start and stop at the same point, there's no width for it. So that's 0 over 0, which means what? Well, it means one thing, right? It means more work. But you know what? It's the good kind of more work. So that's the justification that we need to do l'hôpital. All right, so we're going to apply l'hôpital. Ah, l'hôpital, mon ami. Okay, so this is going to be equal to, all right, and we put a little LH here to say l'hôpital. And you could, of course, be more fancy and say, and now we apply the rule of Mr. Le Hospital. But no, it's okay. You can just say l'hôpital, LH. Apply l'hôpital. All right, now the good thing is, it's when we apply l'hôpital, it's still a limit. Don't forget to write down the limits. They are very picky about this. If you stop writing limits down before you're done, you'll lose a point. You don't want that. It's not a quotient rule, so you take the derivative of the top and derivative of the bottom. Now, the derivative of x cubed, easy. The derivative of the top, we should take a second and talk about that. How do you take the derivative of something like the integral from x to 3x of sine of t squared? Well, that looks like you have an integral, and then you're taking a derivative. Well, is there something that connects derivatives and integrals? Both these ideas seem very fundamental to the subject of calculus, so it would be nice if there was something that connected them. And there is, the fundamental theorem of calculus. So let's remind ourselves of that. All right, so fundamental theorem of calculus, it says what? Well, it says the derivative of the integral from a to x of f of t dt is equal to f of x. All right, well, that's actually kind of simple. And really what we can think of is that when we take an integral, it's an antiderivative. And so if we have an antiderivative and then take the derivative, we should get back to where we started. Sort of like we jump and we jump back. All right, but we can go a little bit further, which is to say we can take fundamental theorem of calculus, mix in a little bit of the properties of integration, mix in a little bit of chain rule, and we have the following, which says, suppose you have a derivative of the integral from h of x to g of x of f of t dt. Well, then this is f of, right, because the derivative of the outside is f. Now chain rule says plug the inside in, so g of x goes in, times the derivative of the inside. All right, so that's the top. When you think of integration, you know, it's like plug in the top minus plug in the bottom. So minus f of h of x times h prime of x. All right, so here we go. Back to our regularly scheduled problem. What were we doing? Well, we're taking the derivative of the top. And that's this piece right here. So it says we're going to plug in 3x in for t. So that would become sine 3x quantity squared, which I can write as 9x squared. And then we're going to times that by 3. And now we're going to subtract, and we're going to plug in the x, which is going to become sine. So everywhere where we see a t, put an x, x squared times the derivative of x, which is 1. All right, now you have two options. One is keep doing l'hôpital, or two, remember facts. Okay, so which one do you want to talk about first? Because I want to show you both. And okay, so let's do our little facts one. So recall, we'll do it down here. So recall that the limit as blah goes to 0, sine of blah over blah Okay, do you remember this? Does what? It goes to 1. Okay, so let's look at our pieces here. So the first part, we have a limit as x goes to 0. I'm going to think of these as two separate pieces. Now, here, if we cover up this part, the 3's cancel. So we really have a sine of 9x squared over x squared. That's the first part. We're still working on that. Now, I want the downstairs to match the upstairs. I have 9x squared for my blah. Here I just have x squared. Well, that's okay. We can fix that. We'll put a 9. But look, if we put a 9, we also need to have another 9 to compensate. So it'll be like 9 times sine of 9x squared over 9x squared. Okay, now that's that part. Then we're going to subtract over here. What do we have? Well, we have sine of x squared. And then downstairs we have 3x squared. So I'm going to think of that as an x squared, and then I'm going to put a 1/3 out in front. So, why? Because I want sine blah over blah. And now our great aha. This part goes to 1. And this part goes to 1 because of our recall, our nice basic fact. And so we end up with 9 minus 1/3. Well, of course, you can multiply 9 times 3 over 3. You get 27 minus 1, which is 26 over 3. Okay, so there we go. That's if you're like, I only want to do one l'hopital. But let's suppose we don't. And let's say, I forgot that fact. What do you do? Well, let's continue our regularly scheduled problem. And we say, well, what's happening here? Well, plug in 0. Sine of 0, 0. Sine of 0, 0. And there's 0. So this is going to 0 over 0, which means more work. Okay, no surprise. So what are we going to do? We're going to take a derivative. All right, so we apply. L'hôpital, mon ami. Okay, so here we go. Derivative downstairs, 6x. Upstairs, well, derivative of sine is cosine. And so we're going to have 3 times cosine of 9x squared times by the derivative of 9x squared. Okay, so that will become 3 times 18, which makes 54x cosine 9x squared. Whew. Okay, so there's a lot going into that 54. There's the 3 and then the derivative of 18x. The sine of x squared, that's a little bit easier. Derivative of sine is cosine, and then chain rule has the 2x. 2x cosine x squared. Now, what does this do? Well, you say, okay, let's plug in. And we plug in 0, and we see these zeros. And there's a 0. So this goes to 0 over 0, which means more work. All right. Wow. Just when we thought it was done, more work pulls us back in. All right, that's okay. We're almost there. The end is in sight. So, why do I say that? Well, let's think about it. Look at your denominator. What happens when you take the derivative of 6x? You get 6. And this one we're like, game over, man. Game over. Because that's not 0 or infinity. It's a number. So whatever happens, happens right now. There's no more work after we have to finish this work, but there won't be any more L'Hopital's rule. This will be it. All right, so as we prepare ourselves mentally for the upcoming derivatives, we're going to have product rule. All right, so here we go. 54x, well, we have 54 cosine 9x squared. So the derivative of the first times the second, plus 54x times the derivative of cosine 9x squared, which is minus sine 9x squared times 18x. Now, we don't have to simplify it because we're about to plug in. So because we're not taking any more derivatives, don't worry about simplifying. Minus the derivative of the first, well, that would be 2 cosine x squared, and then minus 2x times the derivative of cosine x squared, which is minus sine of x squared times 2x. All right, now plug in 0. We get 54 cosine of 0, 0, plus 0, right, because of that 0, 0, 0, minus 2, because cosine of 0, 0. And then here, minus 0, all over 6. Well, that's the same as 52 over 6, which top and bottom has a factor of 2. And so you say, that's the same as 26 over 3. So 26 over 3. Same as what we had before. Well, yeah, it's just a different way. So sometimes we get so excited about le hôpital. We get to say like, le hôpital, mon ami. And we get so excited doing that, we can forget, there are other things that we learned. And there's other tools at our disposal. And the more tools that we have, and the more tools that we use, the better the problems are. And the more successful we can be in solving them. Find the following. The integral, now it's an indefinite integral, no bound, so we have to end up with thetas at the end, so don't forget that. Cosine cubed of theta, square root 2 minus sine theta d theta. Okay, well, now, we look at this and say, what do we do? Well, we ask ourselves, is this something that we recognize? In other words, is it one of our 8 or 10 or so basic integrals? No, it's not. Could we apply some algebra? Not really. Could we apply trig? Well, about the only thing that we have, a trig identity, because everything says theta on the inside, so we don't need any double angular power reduction. We don't want to do that. We do have a cosine squared plus sine squared equals 1 in our back pocket, so we'll make a note of that. Who knows, that may or may not come in handy. It's always handy to have whenever you see sines and cosines. And so we'll say cosine squared plus sine squared equals 1. Well, okay, so what's the next thing to look for? Well, the next thing to do is to say, well, what about like a substitution? Substitution is one of our go-tos. And oftentimes, when we see a problem, as soon as we don't recognize it, we start kind of like, hey, can we start moving towards a substitution? Now, we haven't had our substitution talk in a while, so let's have our substitution talk. When we're thinking about substitution, what are we thinking about? Well, we have an integral of f of, and I'm going to choose some colors here because I like to make things colorful, g of x, and then we have on the end a g prime of x dx. Okay, so this will become, when we make our substitution is that we have u equals g of x, and then on the other hand we have that du equals g prime of x dx. And we say, okay, great. So once we carry out this substitution, well, this becomes the integral of f of u du. It's a little bit easier to sort of work with. Now, when we're thinking about this, we start saying, okay, where do you look for substitutions? And there's always sort of one place that people really focus on, but it's good to remember that there's sort of two coming into play and they interact with each other. So the one that people give the most attention to is the inside. Substitution is an inside job. We're looking for something on the inside, something in another function. Simultaneously, we want to remember that, and don't forget, look for the derivative. Do you see a matching derivative? And maybe if it's not an obvious candidate for what's on the inside, this might be a good clue. So for us, do we see sort of a clear, hey, that's on the inside, we should look there? Well, we do. and that is that 2 minus sine theta. That's inside the square root. So we say, okay, let's make that our substitution. So all right, great, no worries. We're going to try u equals 2 minus sine theta. Now, if we do this, what do we get for du? Well, du would be derivative of minus, well, the 2 goes away, derivative of sine minus cosine, minus because of the minus sign. Derivative of sine is positive cosine, and d theta. And now we say, do we have a cosine available to us? And we say, yes. If anything, we have an overabundance of cosines available to us. And that might pose a challenge to us. So let's think about this for a second. Before we finish this substitution, let's talk about what's going to happen. So we see there are 3 cosines here, because it's a cosine cubed. We only need 1 cosine for the du. So if we think about this, and I'm going to move this, so minus du equals cosine theta, we really have a cosine squared theta. And here I'll write this in a more calculus-friendly way, 2 minus sine theta to the 1/2. And I'm going to put a cosine theta on the end. So I pulled off a cosine theta. So this part we're happy with, because this is going to become our du. This part we're happy with, because this is going to become our u. Now this part we need to think about. Here's the thing, is we can't replace just half of it. We've got to replace all of it. So every single occurrence of theta has to go away. There can't be any thetas left, and there can't be any cosine squared thetas left. And so at this point we're like, what can we do? So this is the part which makes this one a little bit tricky. And we start saying, well, you know, basically our u looks like our sine. In fact, we can note this. We can say, hey, this is the same thing as saying that sine of theta is 2 minus u. And so we say, well, that would be great if these were sines, not cosines. And now is when we reach into our pocket and say, oh, but hold on a second. A sine squared is basically a cosine squared. That's what this says. If you say, look, if you know sine squared, it's a cosine squared and vice versa. Ooh, so this suggests a plan. So what's the plan? Well, the plan is that this cosine squared, we can replace it by 1 minus sine squared. Good, good. We're starting to fill it. Okay, but now that sine, each sine becomes a 2 minus u. So this becomes 1 minus 2 minus u squared. And now we're good. So we have a way to replace that. Okay, so let's put it all together. So we now have the following. With this substitution, this becomes the integral, that cosine squared, 1 minus 2 minus u squared. This square root of 2 minus sine theta, u to the 1/2. And this cosine theta d theta becomes, don't forget the minus, a minus du. All right, now the good news is this is algebra. And you know, that's great news. We love algebra. Okay, so let's see what this becomes. All right, so we're going to start unraveling here. And this first part, let's expand this. So this is 1 minus 4 minus 4u plus u squared times u to the 1/2 times minus 1. Okay, I guess okay, sure, I'll just rewrite the whole thing. Why not? Then this becomes, so distribute the minus and combine. So we have a minus 1 minus 4 is minus 3. And then minus 4u makes plus 4u. And then minus u squared. All right. U to the 1/2. And then again, there's a minus 1. Well, now let's multiply the minus u to the 1/2 through. Okay, so this becomes integral of 3 u to the 1/2, right, positive 3, minus 4 u to the 3/2, okay, and then plus u to the 5/2. Aha! Yes, this is perfect. These are wonderful things to integrate. Oh, kapla! Which, of course, we all know means success in Klingon. Okay, now, wow, cool. It's looked almost impossible, and now it's like, what? This is great. This is the kind of integral we take to meet the family. Or, at least show them a picture of, hey, this is this cool integral I met when I've been in my classes. Okay, so let's integrate term by term. So the 3, u to the 1/2, we add 1, that's to the 3/2 power, right? 1 plus 1/2, 3/2, and then times it by 2/3 in front. Minus 4, add 1 becomes 5/2 times by 2/5. Then add 1 here, that would be u to the 7/2 times by 2/7. And of course, add your c. So we have 2u to the 3/2 minus 8/5 u to the 5/2 plus 2/7 u to the 7/2 plus c. Good. And are we done? No. Oh my, wait, but we integrated. What's left? We got to go back to where we started. Okay, all right. So where did we start? We started with thetas. We have to end with thetas. And so we say, okay, how did we start? Well, we started with this u equals 2 minus sine theta. So everywhere we see a u, we're going to put in a 2 minus sine theta. So our final answer will be 2 times 2 minus sine theta to the 3/2. And, gotta make that look like a 3. And, all right, minus 8/5, 2 minus sine theta to the 5/2 plus 2/7, 2 minus sine theta to the 7/2 plus c. And that is our answer. All right, good, good. Phew. Now, you probably were not expecting the answer to look like this, and that's okay, because we don't need to know what things look like from the beginning. We work the process, right? Think about your substitution. Remember, you got to replace everything. So that's cosine cubed. How do you turn that into something you can work with? Well, okay, part of it goes to du. Part of it, use your identities and think about what things become. All right, well, that was a good one. A nice, fun problem. Let f of x equal the integral 1 plus x to 3 minus x of f of d dt, where f of t is the function shown below. So we have a line, goes up, down, and then flat again, right? Shoop, 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 shoop. Okay, so there we go. And we're asked to do some various things. So find f of 1. Okay, well, that's not so bad. What do we do? Well, plug in 1. So this is integral from 1 plus 1 is 2. 3 minus 1 is 2 of f of t dt. And integral from 2 to 2? Well, that says we're going to start at 2 and go to 2. And what's the area there? Not a lot of area. It's equal to 0. All right, so if you ever see these points match, 0. All right. Whew. Wow. Now, in a wonderful world, this would be worth half the points. I suspect this would be worth like 1 or 2 points. I think part B is going to take us longer. Find the tangent line to the function y equals f of x at x equals 0. What? Oh my God. What? Okay, all right. I think this was a problem that Steve wrote. You know, it just classic Steve. All right. Come on, we'll back up. We won't panic. We'll start unraveling. Okay, so if we're after a tangent line, what pieces of information do we need? Well, we need to know the value of the function and the value of the derivative. So for a second here, let's just call this g of x. So we need to know what is g of 0 equal, what is g prime of 0 equal, and if we have that information, then we'll have our line. Okay, because essentially tangent line is more or less saying there are two things. What's happening with the function, what's happening with the derivative. If we answer those two questions, we have our tangent line. Well, let's start with plugging 0. Okay, so let's start up here. Shloop. What is f of 0? Well, to answer that, let's start by talking about f of 0. So f of 0 would be the integral from 1 up to 3 of f of t dt. All right, so we can look at this and we have the picture. So 1 to 3. So let's mark this. So here we are. 1 to 3. Now, we just need to figure out the area because the integral is an area. And we can count the squares. There's 1, 2, a half, and a half. And so that is 3. So this is geometry. That's how we figured out the answer to that. Okay, so we say, great, f of 0, that's the same as f of 3. Whew. Phew. Good. So what is f of 3? Well, all right, what is f of 3? And, well, plug in. So we're going to go integral 4 to 0 of f of t. Now, you might notice something a little bit strange about this. The bounds seem out of order, and that's because the bounds are out of order. We normally go from a low number to a high number. So what happens when that doesn't happen? Well, we switch, but when we switch the bounds, it's essentially switching in orientation, which means you have to put a minus sign. So this is minus integral 0 to 4 of f of t dt. All right, so now we're going to go from 0 to 4, and let's see, do we have another color? Maybe here. So 0 starts here. 0 includes what we've already shaded up to 4. All right, so what do we have now? Well, we just need to do some counting here. And so we have, again, 1, 2, 3, 3.5, 4, 4.5. So that says f of 3 is going to be minus 4.5 or 9 halves. Okay, so minus 9 halves. Which means, going back to our tangent line, g of 0, negative 9 over 2. Cool. We're halfway to our tangent line. Now, we need to talk about g prime. Okay, well, let's do it. Let's talk about our g prime. Well, what can we say? Well, we can apply our various rules and say g prime of x is, so chain rule. Yeah, function inside function. F prime of f of x times f prime of x. Yes? All right? Take the dirt of the outside, plug the inside in, times the dirt of the inside. All right. So we know that. Now, what does that tell us? Well, we can say, look, that tells us that g prime of 0, because we want g prime of 0, that's equal to f prime of f of 0 times f prime of 0. Now, we also did some work before that says we know what f of 0 is. F of 0 is 3. So this is f prime of 3 times f prime of 0. And now we're like, cool, we're in the home stretch, right? Because all we have to do now is multiply those derivatives together. And how do we get them? Okay, all right. So we need to take the derivative of f. And we've talked about it before, so we're not going to go into a lot of detail again, but what we need here is the fundamental theorem of calculus. Fundamental theorem of calculus plus chain rule. So here we go. The fundamental theorem of calculus plus chain rule tells us the following. It says that capital F prime of x is equal to, we're going to take f of, plug the top in, 3 minus x times the derivative of the top, so times minus 1, plus f of 1 plus x times the derivative of 1 plus x. Oh, sorry, not plus. This is a minus, excuse me. 1 plus x times the derivative of the inside, which is 1. Right? So it's plug in the top times the derivative of the top minus plug in the bottom times the derivative of the bottom. Or, if you like, this is minus f of 3 minus x minus f 1 plus x. Okay, so we almost have enough space to finish this off, and we're going to do it. I have faith that we're going to succeed. Okay, so for us, let's talk f prime of 3. We'll start there. So this is minus 3 minus 3 is 0, so f of 0 minus 1 plus 3 is 4. So we come to our diagram. F of 0 is 1. So this is minus 1. F of 4 is 0. So minus 0. So that makes a negative 1. Okay. Now, that's f prime of 3. Okay, so this equals negative 1 times, what is f prime of 0? All right, f prime of 0. Come up to our diagram. And according to this, we're going to have minus f of 3. Sorry, I was pointing to the wrong place. F of 3 minus f of 1. Okay, that's what happens when we plug in 0. F of 3 and f of 1. Okay, f of 3 is 1. So that makes minus 1. Subtract. F of 1 is 1. Minus 1 makes minus 2. So we have minus 1 times minus 2, also known as 2. All right, so we have 2. All right, so that's g prime of 0. Okay, so now we have our value of our function and our slope. So we put them together. So y is equal to our function minus 9/2 plus our slope 2 times x minus 0, which is 2x. And there we go. Minus 9/2 plus 2x. Just like you thought, right? Well, maybe not just like you thought, but that is what's going on. All right. Wow. What an interesting problem. And lots of pieces, but of course, just be methodical. Know your facts. You know, if the bounds agree, you're 0. If the bounds are out of order, put a minus sign. Use your chain rule. Use your fundamental theorem of calculus. And so oftentimes, big problems look too intimidating. It's like, how can we possibly do big problems? Well, they're secretly just lots of small problems put together in disguise. Breaking it into smaller, bite-sized pieces. You have all the tools to succeed, and you can succeed. Practice, practice, practice. Think how it all fits together. You'll be okay. I believe in you. And we still get one more problem to go. All right, more fun. Woohoo! Our last problem. And look how short it is. That must mean it's going to be pretty quick, right? Right? Well, let's see. We're going to evaluate the integral from 0 to 1 of the square root of x minus x to the fourth dx. Okay. Well, there's no trig, so that's something. It's not one of our 8 problems that we know how to do automatically, one of our 8 integrals. So that's kind of out. And so we start saying, okay, well, we've got algebra and substitution. Now let's think about substitution. Is there a good substitution right now? Well, just x doesn't do anything, so it has to be more complicated than x. If we tried x to the fourth, well, the problem is we don't have like a x cubed on the outside. X minus x to the fourth, well, that would be like a 1 minus 4x cubed. That's even worse. Okay, so we're not really feeling the substitution vibe yet. Okay, but what's the algebra saying? Well, notice you have both terms have an x involved. So we could say, hey, this is really the same as the square root of x times 1 minus x cubed. And all right, and we can pull it apart into 2 pieces. So we can say, okay, this is really square root of x and square root of 1 minus x cubed. All right, now, what kind of substitution can we make? Well, we can say, now separated, 1 minus x cubed. That might be a good substitution. Well, what's the derivative of 1 minus x cubed? 3x squared. Do you have a 3x squared outside? No. Okay, well, what about square root of x? Well, what's the derivative of square root of x? 1 over square root of x. Okay, so let's recall our substitution discussion. We had one earlier, so this is going to be a short one. Recall that when we're thinking about making substitutions, there's 2 places to look. And so oftentimes we get hung up on looking for what's the inside function, that we get distracted and say, hey, there's this second place to look, which is what's the derivative. So when we're talking about looking for a substitution, that shouldn't have been a g prime of x, that's just a normal g of x. There we go, there we go, g of x, g prime of x. So we oftentimes get hung up by saying, look for the inside, but we should also say, don't forget, you can also say, do you have something which is a nice derivative? In other words, is there at least a tiny sliver that you can integrate? Well, look here. We can't integrate that. We can't do anything here. Square root of 1 minus x cubed, kind of hopeless. Can you integrate square root of x? You can't. What is the integral of square root of x? So what I'm trying to get at is, what if we think of this as our g prime? In other words, we're thinking of that as the derivative of our substitution. So work it backwards. Square root of x is x to the 1/2. The integral of x to the 1/2 is, don't worry about the constant in front, it's x to what power? 1/2 plus 1, 3/2. So if we're thinking of this as corresponding to our g prime, this is suggesting try x to the 3/2. Because, as we said, the derivative would be 3/2 x to the 1/2. So this becomes part of our du. Now, you might say, Steve wrote something down. He must think this is a good substitution to try. Well, yeah, because there's not a lot of options. And but notice something else. What's going on here? Well, when we look at what we have the integral, the square root of x dx, that becomes a 2/3. I'll go ahead and pull the 2/3 all the way out. Du. What can we do with this x cubed? Is there any relationship between x to the 3/2 and x cubed? Yes. If you square x to the 3/2, you get x cubed. So this becomes the square root of 1 minus u squared. Now, this is a definite integral, which means we need to update the bounds. You always update the bounds when you go forward. That way you never have to go back. So if we update our bounds, then we're going to have something easier to work with. So remember, these are x bounds. These are not u bounds. So it's currently going from x equals 0 to x equals 1. So these are not the bounds for u. So these are not the u bounds. We are not going from 0 to 1. We're going to go from 0 to 1. Very good. All right. Now, I want to emphasize something actually did happen here. So what happened? Well, you have to update the bounds. So notice we have x to the power. Plug in 0. 0 to the power 3 halves is 0. 1 to the power 3 halves is 1. So it wasn't like, oh, we just copied it down. We actually did check and said, hey, what's happening to our bounds? All right, so we get 2/3 integral of 0 to 1 square root of 1 minus u squared. Was this a good substitution? I claim yes, because it's simpler. The goal of math in general, and in calculus in particular, boils down to, can you keep making things simpler to the point where it's so simple, it's the answer. And this is a lot simpler. Now, I don't claim trivial, but simpler. Unfortunately, it's still not one of our integrals that we know right away. But there's a familiar ring to this integral, like we've seen something like this before, somewhere out there, beneath the pale moonlight. What do you see? Well, let's try to sketch it. Maybe if we sketch it, we'll have our memory recalled. So we'll say y equals the square root of 1 minus u squared. That's y squared equals 1 minus u squared. Oh, wait a second. That looks like u squared plus y squared equals 1. Wait a second. That's a circle. Now, we're not after the whole circle. We're only going from 0 to 1. And we're only the top half. And so we say, the integral is finding this area. And we're like, oh. So we can do geometry, because we know an integral represents a total, and we can interpret it as a total area. We say, hey, this is really the 2/3 in front times how much area is here. Well, it's 1/4 of a circle, and then the area is pi r squared. Right? So this is 1/4 of a circle of radius 1. And we say, okay, great. So we're done. We did the integral. We did the integral without actually doing the integration. We did the integral by knowing what it represented. Well, we're basically free. We can do a little bit left. 2/3 times 1/4. You can cancel off a single 2. So you end up with 1/6 and then times pi. 1/6 pi. All right. And there we go. There's our final answer to our final problem. We made it. Woohoo! Yes! Ha! Now I want to give you some notes. You're probably walking away, especially from the last couple of problems, and be like, oh my gosh, is the exam going to be this hard? Not this hard. It's not going to be trivial. I'm not going to lie to you. We give you challenging problems to practice so that when you see problems that are not easy, but little mildly challenging, you'll be ready. It's like you go to them, you lift heavy weights so that you can go and do the problems that move things in real life that you might have to do. So don't panic, right? Work the problems. And if you came from this and said, man, these were all easy, wonderful. And if you didn't, that's okay. You have time to practice. Prepare yourself. You can do well. You're amazing. And I'm appreciative of all the effort you're putting into this to help yourself succeed. And I hope all the best for you. I hope everything goes well. And let's see each other on the other side. All right. Good luck. Bye.